On the night of July 24, 1943, just after midnight, in a concrete bunker on the German coast near Hamburg, a Luftwaffe radar operator was watching his screen do something it was not supposed to do. He had been trained to look for aircraft, discrete points of light, returning radar echoes from the metal hulls of British bombers as they crossed into German airspace. He had seen those points before. He had vectored Messerschmitt night fighters onto them. He had watched them disappear from the screen when his fighters did their work. The system functioned. For 3 years it had been functioning. The Kammhuber Line, of which his radar was one small node, had been killing Royal Air Force bombers at rates that the RAF could not sustain. What he was looking at now was not a point of light. It was a wash, a snowstorm of false echoes that filled the screen from one edge to the other, dense enough that no individual aircraft could be picked out of the noise. His Würzburg tracking radar, which had been designed with such precision that it could direct anti-aircraft fire to within a few meters of a moving bomber, was reporting hundreds of targets where there should have been a few dozen. The data was useless, worse than useless. The night fighters circling above Hamburg, their pilots straining their eyes against the dark sky, were getting radio directions that pointed them at echoes that were not aircraft. The anti-aircraft guns below them were firing into empty air. The searchlights, slaved to the same blinded radars, were waving across the night sky with the meaningless motion of a man swatting at insects he could no longer see. Josef Kammhuber, the Luftwaffe general who had built the air defense system that was now collapsing, summarized what had happened in a single sentence after the war. The whole defense was blinded in one stroke. The weapon that had blinded it was not a bomb. It was not a new aircraft. It was not a secret electronic device requiring a vast industrial program to manufacture. It was bundles of aluminum-coated paper strips, 27 centimeters long, 2 centimeters wide, cut to a precise length that the British had calculated from German radar wavelengths captured 18 months earlier in a commando raid on the French coast. Each bomber dropped them by hand through a flare chute at 1-minute intervals on a stopwatch. The simplest piece of physics imaginable, weaponized into an electronic weapon that the most sophisticated air defense network in the world could not defeat. This is the story of how that piece of physics was discovered, why both sides knew about it for years and refused to use it, what happened the night the British finally used it anyway, and why German operators on the radar screens came to fear the silvery strips falling from the night sky more than the explosives that the bombers carried with them. To understand what Window did, you first have to understand what it was undoing. A German night air defense system that, by 1943, had become extraordinarily effective at killing British bombers. The Kammhuber Line was the work of General Josef Kammhuber, a Bavarian-born Luftwaffe officer who had been put in charge of organizing the Reich's night defenses in July 1940. What Kammhuber built over the next 3 years was an integrated network of radar-controlled interception zones running from Denmark down through the Low Countries to the middle of France, with additional concentrations around major German cities. The system depended on layered radar coverage in carefully overlapping cells, each cell roughly 32 kilometers north to south and 20 kilometers east to west. Each cell was called a Himmelbett, a German word that means canopy bed or four-poster bed, because the system enclosed the airspace above it in a way that, on a map, looked vaguely like the boxed framework of a canopied piece of furniture. Inside each Himmelbett, 3 radars were doing different jobs. A long-range Freya early warning radar, with detection out to roughly 100 kilometers, watched for approaching aircraft. When the Freya picked up a bomber, 2 shorter-range Würzburg tracking radars took over. One Würzburg locked onto the bomber, the other locked onto a German night fighter that had been scrambled to intercept. Both radars fed their position data to a control center, where a fighter director officer used voice radio to vector the night fighter toward the bomber. When the 2 aircraft were close enough, typically within a few thousand meters, the night fighter's own short-range Liechtenstein airborne intercept radar took over, guiding the pilot to within visual range of his target. Then he opened fire. The system worked. By the middle of 1942, with airborne intercept radar coming into Luftwaffe night fighter service, Bomber Command's loss rates were running at roughly 4 to 5% on major raids over Germany, and analytical studies inside Bomber Command set the threshold of sustainability at somewhere between 5 and 7%. Above that, the force would be wearing itself out faster than crews and aircraft could be replaced. Some individual raids on heavily defended targets pushed losses well into the double digits. The Luftwaffe night fighter force, working through Kammhuber's system, claimed over 6,000 RAF bombers between 1940 and 1945. The Liechtenstein-equipped ace Heinz Wolfgang Schnaufer alone shot down 121 RAF aircraft over the course of his career. For the men flying the bombers, the experience was specific and terrifying. You crossed the channel in darkness. You crossed into German-controlled airspace. You knew somewhere below you, 3 radar dishes were quietly turning toward you. You knew that at some point in the next minutes, a German night fighter pilot you would never see, vectored by a controller you would never hear, would close to within firing range of your aircraft from below and behind. The first sign of contact, in most cases, was the sudden hammering of 20mm cannon shells through your fuselage. Aircrews talked about the German fighters the way Pacific submariners talked about depth charges. There was no way to evade what you could not see. The only defense was statistical. Fly in a tight enough stream of bombers and hope the night fighters could not find you in the crowd. Bomber Command knew exactly what was happening. The 1942 1,000-bomber raid against Cologne had introduced the concept of the bomber stream, packing aircraft so densely through a few of Kammhuber's Himmelbett zones that the radar controllers, who could only handle 1 or 2 interceptions per cell per hour, became saturated. The tactic worked, partially, but the Germans adapted, and by 1943 the loss rates were creeping back up. Hamburg, the next major industrial target on Air Chief Marshal Arthur Harris's target list, had 15 Himmelbett zones defending it and 9 night fighter bases in its immediate vicinity. Attacking it under conventional tactics would have been suicidal. What Harris had, what nobody else in Europe had, was a weapon that he had been forbidden to use for 18 months. The principle behind window is so simple that it can be explained in a single sentence. A piece of metal whose length is approximately half the wavelength of a radio wave will resonate when the radio wave strikes it, absorbing energy from the wave and re-radiating it in all directions, producing a radar echo that is essentially indistinguishable from the echo of a small aircraft. This was not a discovery that required a Nobel laureate to make. The mathematics of dipole antennas had been known to physicists since the 19th century. A metal dipole half a wavelength long in an electromagnetic field at the right frequency behaves like a small reflective object several times its actual size. If you drop hundreds of such dipoles into the air, with their orientations randomly distributed and their positions scattered across a few cubic kilometers, you produce a cloud of radar reflections that, on a 1943 radar display, looks identical to a formation of large aircraft. The trick was knowing the wavelength of the enemy radar. The British had a head start on this. Through the late 1930s and early 1940s, British scientific intelligence, coordinated by a young Air Ministry scientist named R.V. Jones, had been quietly mapping the German radar network from a combination of leaked documents, decrypted Enigma signals, prisoner-of-war interrogations, and direct reconnaissance. Jones had identified the Freya long-range radar by 1940. He had identified the Würzburg tracking radar by November 1941. He knew by early 1942 that German radars were operating in 3 major frequency bands, all of which were susceptible in principle to dipole-based jamming. What he needed was confirmation of the precise frequencies. That confirmation came on the night of February 27 and 28, 1942, when British commandos under Major John Frost landed at Bruneval on the French coast, dismantled a Würzburg radar installation, brought back the key components by sea, and delivered them to telecommunications research establishment scientists in Britain. The captured Würzburg told the British everything they needed to know about German short-range tracking radar frequencies and confirmed that aluminum strips cut to roughly 27 centimeters in length would resonate inside its operating band and saturate its display. The development of the actual countermeasure was led, in Britain, by a Welsh physicist named Joan Curran. Born Joan Struthers in Swansea in 1916, she had won a scholarship to Newnham College at Cambridge in 1934. Completed an honors degree in physics in 1937, though the university did not at that point award degrees to women, and then gone to the Cavendish Laboratory to begin doctoral research. War work intervened. She married fellow physicist Samuel Curran in November 1940, and the two were transferred together to TRE, where Sam worked on centimetric radar while Joan joined the countermeasures group, first at Swanage and later at Malvern. It was there, working through 1941 and 1942, that she developed the countermeasure that would become window. She tried various forms of reflector: copper wires, sheets of metal, leaflets the size of notebook pages that could have done double duty as propaganda, before settling on the configuration that would become the operational design: thin strips of aluminum foil bonded to black paper, cut to a length of 27 centimeters and a width of 2 centimeters, packed into bundles of approximately 1 pound weight. The paper backing reduced the weight, allowing the strips to drift longer in the air before settling out. The aluminum did the radar reflection. The head of TRE, A.P. Rowe, gave the device a deliberately uninformative code name, Window, chosen for security reasons with no obvious connection to the function. Across the North Sea, German scientists had independently arrived at the same idea and given it their own code name, Duppel, after the Berlin suburb where the early experiments had been conducted. By 1942, both sides of the war knew that aluminum strips could blind their enemy's radar. Neither side dared use them. The reason the British did not use window in 1942 and the reason the Germans did not use Duppel in 1942 was the same reason on both sides, and it has the perfect shape of a Cold War standoff 15 years before the Cold War. The British scientific advisor, Professor Frederick Lindemann, Churchill's personal scientific advisor, an immensely powerful figure in the wartime scientific establishment, had pointed out the obvious risk in cold mathematical terms. If the Royal Air Force used window against German radar, German scientists on the ground would pick up the aluminum strips within hours, understand them within days, and replicate them within weeks. As soon as they replicated them, they would drop them over Britain, and Britain's own chain-home radar system, which had defeated the Luftwaffe in the Battle of Britain in 1940, would be just as blinded as the Kammhuber Line. The Battle of Britain had been won by a thin margin. The chain-home radars had given Fighter Command roughly 20 minutes of warning before incoming German raids, which had been just enough to scramble interceptors. Without that warning, the British air defense system in 1942 could not have held. The RAF's Fighter Command and Anti-Aircraft Command, recognizing the stakes, lobbied hard to keep Window grounded. Lindemann's argument prevailed. Window stayed locked in a TRE warehouse. On the German side, Hermann Göring had reached the same conclusion through the same logic. German scientists had perfected Duppel in 1942, possibly slightly later than Curran perfected window, but close enough that the two countries arrived at operational capability in roughly the same window. If Germany used Duppel against British radar, the British would copy it within weeks and use it against the Kammhuber Line, which the Luftwaffe was investing enormous resources in expanding. The Duppel research files were classified at the highest level, and Göring personally prohibited their use. The German radar industry was forbidden from even discussing the concept openly. For most of 1942 and the first half of 1943, both sides held their breath. Each had a device that could devastate the other's air defense. Each refused to use it for fear of triggering its use by the other. The standoff was not a treaty. It was not negotiated. It was simply the rational behavior of two scientific bureaucracies, each looking at the same physics, each understanding the same consequences, each independently deciding that the cost of unilateral disarmament was lower than the cost of breaking the standoff first. What broke it in mid-1943 was a shift in the balance of vulnerabilities. By July 1943, the bulk of the Luftwaffe bomber force was operating against the Soviet Union in the east. German bombing raids against Britain had largely ceased. The 1940-style blitz that Lindemann had feared was no longer a credible threat. Meanwhile, the British strategic bombing campaign over Germany was reaching peak intensity, and Kammhuber's night defenses were inflicting losses that Bomber Command considered unsustainable. The calculation reversed. The risk of triggering a German response to Window was now smaller than the risk of continuing to fly over Germany without it. On July 15, 1943, the British War Cabinet authorized the operational use of Window. The first opportunity to use it came 8 days later. Arthur Harris had a target waiting. There was one further consideration that tipped the balance, and it concerned the British technological lead in centimetric radar. By mid-1943, the British had operational ground and airborne radars working at wavelengths around 10 centimeters, derived from the cavity magnetron developed at Birmingham University in 1940 and shared with the Americans on the Tizard mission in 1940. Those centimetric radars were not vulnerable to the standard window strips, which had been cut to resonate with German meter wave and decimeter wave equipment. If Germany retaliated with its own duple, the British air defenses could continue to operate on their centimetric systems while the German systems remained crippled. The asymmetric vulnerability was now real, and it favored the British. The decision to use Window was, in the end, less a risk than the 18 months of caution had been making it appear. The plan was called Operation Gomorrah, and the target was Hamburg. Hamburg was, by any military measure, an ideal strategic target. Germany's largest seaport, a major shipbuilding center, home to the Blohm & Voss yards that built U-boats, aircraft engine plants, oil refineries, a population of approximately 1.5 million people, and it sat near the North Sea coast, putting it within range of British bombers operating from East Anglia and southern England. Harris planned to attack it across multiple consecutive nights, a sustained pressure that would, if it worked, demonstrate that Bomber Command could destroy a major German industrial city in a single concentrated campaign. The defenses were formidable. 15 Himmelbed zones in immediate proximity, 9 night fighter bases within easy reach, 56 heavy and 36 light anti-aircraft batteries inside the city. A radar-controlled air defense system that, on paper, should have inflicted catastrophic losses on any sustained attack. Harris's plan was simple in concept and exquisitely choreographed in execution. On the night of July 24-25, 1943, 791 British bombers would take off from English bases and fly toward Hamburg in a tight stream. Each bomber would carry, in addition to its bomb load, a quantity of Window. 24 selected lead crews were briefed in detail on the deployment technique. Drop a 1-pound bundle of strips through the flare chute every minute, timed by stopwatch, beginning as the aircraft crossed the enemy coast. The rest of the stream would follow the same protocol. By the time the formation reached Hamburg, the air behind it would be filled with a continuous corridor of slowly descending aluminum, refreshing itself faster than the strips could fall. The first bundles went into the night sky shortly after midnight. About half an hour past midnight on the morning of July 25th, 7,000 bundles of Window had been scattered across the radar field of the Hamburg defenses. The effect on the radar screens below was instantaneous. The Würzburg tracking radars, designed to lock onto a single aircraft with high angular precision, locked onto everything. The Freya early warning radars, which had been showing a coherent bomber stream advancing on Hamburg, now showed a wash of false echoes spread across hundreds of square kilometers. The Liechtenstein airborne intercept radars in the German night fighters, when their pilots tried to use them, showed the same chaos. The night fighters could not be vectored because the ground controllers could not find them on their screens. The fighters that found themselves over Hamburg by dead reckoning could not lock onto targets because their own onboard radars were showing the same snowstorm. The bombers came in. The fires started. Hamburg, on that first night, suffered the most concentrated bombing attack in the history of warfare to that point. Of the 791 bombers dispatched, only 12 were lost, a loss rate of about 1.5%, well below the threshold that Bomber Command considered the limit of sustainability. The night fighters that should have been killing British aircraft at 5% per raid had killed almost none. The anti-aircraft guns, firing without radar guidance, had fired into empty sky. Across 4 nights of attacks between July 24 and August 2, 1943, the campaign continued. Bomber Command dropped roughly 9,000 tons of high-explosive and incendiary bombs on Hamburg. A firestorm developed on the night of July 27th to 28th, a self-sustaining conflagration with temperatures around 1,000 degrees Celsius and winds of hurricane velocity drawn into the burning city. Most sources put the civilian death toll at around 42 to 46,000, with some older estimates reaching as high as 125,000. Roughly 1 million people fled the city in fear of further attacks. Albert Speer, the German Minister of Armaments, later said that if 6 more cities had suffered the fate of Hamburg, German war production would have broken down. The figure was probably an exaggeration. The fear behind it was not. Kammhuber's sentence, summarizing the radar failure, has become the defining sentence of this episode. The whole defense was blinded in one stroke. The German response to Window followed, in the weeks and months after Hamburg, the predictable path of any side that has just been struck with a new weapon. First, denial. The German civilian population, who picked up the aluminum strips in the days after the Hamburg raids, did not immediately understand what they were. Rumors circulated that the strips were carrying poison or disease. The Luftwaffe High Command issued statements minimizing the damage and emphasizing the casualties inflicted on the bombers. The official tally of British losses was inflated. Second, retaliation. 6 weeks after Hamburg, on the night of October 7th to 8th, 1943, the Luftwaffe began dropping its own version of the same device, Duple, over Britain. The German strips were cut to slightly different dimensions, 80 centimeters by 1.9 centimeters, optimized for British radar frequencies. The Luftwaffe used Duple during the limited bombing operations it could still mount against Britain in the autumn of 1943, and most extensively during Operation Steinbock, the so-called Baby Blitz, between February and May 1944. But by that point, the Luftwaffe bomber force was a shadow of what it had been in 1940. The British night fighter force was large, the British radar network had been upgraded to centimetric wavelength that Duple did not jam as effectively, and the limited number of German bombers were vulnerable in spite of their countermeasures. Third, adaptation. Recognizing that the Kammhuber Line's ground-controlled interception system was fundamentally broken in the presence of Window, a Luftwaffe colonel named Hayo Hermann developed a new tactical doctrine called Wild Sau, wild boar. Instead of vectoring night fighters precisely onto individual bombers, ground controllers would simply direct fighters toward the densest concentrations of Window, which, by definition, indicated where the bombers actually were, and rely on the pilots to visually acquire targets against the illumination of fires below and searchlights above. 3 new fighter wings, JG-300, JG-301, and JG-302 were formed to use this technique. Some fighters were fitted with a device called the FUG 350NX, which could home in on the H-2S ground mapping radar emissions from RAF Pathfinder bombers. The new system was crude compared to the precision interception of 1942 and early 1943, but it brought German night defenses back into operational effectiveness within a few months. What Wild Sau and the related adaptations could not do was restore the original Kammhuber Line. The Himmelbett system depended on precise individual radar tracking. Window made that precision impossible. The radars themselves were not destroyed, they continued to function, but their information was no longer reliable enough to vector fighters onto specific targets. The whole architectural premise of the original system, which had taken 3 years and enormous industrial resources to build, was now a degraded shell of what it had been on July 23, 1943. The deeper German problem was that the technical countermeasure to Window required a generation of new radar technology that Germany could not develop quickly. Centimeter radar, operating at wavelengths short enough that the existing window strips would not resonate effectively, was the obvious answer. The British had centimeter radar already, based on the cavity magnetron developed at Birmingham University in 1940. The Germans did not. German radar industry through the war operated mostly at wavelengths in the meter and decimeter ranges, susceptible to the same window strips that had blinded the Würzburg over Hamburg. By the time German engineers began developing centimeter systems in 1944, the war was effectively decided. The Liechtenstein SN2, a longer wavelength airborne intercept radar that was less vulnerable to the original window strips, was rushed into service in late 1943 and gave the German night fighters a partial reprieve. The British responded by manufacturing window in different lengths optimized to the new SN2 wavelengths. The countermeasure cycle continued through 1944 and into 1945, but the German side was always one step behind, perpetually responding to British innovations with adaptations that took longer to produce than the British took to develop the next round of countermeasures. While the British were perfecting window in 1942 and 1943, an American program had been working on the same problem in parallel with characteristic differences of scale and approach. The American work was based at Harvard University's Radio Research Laboratory, established by Stanford electrical engineer Frederick Terman in early 1942 to develop electronic countermeasures for the U.S. Air Forces. Terman had visited Britain shortly after his appointment and seen the British work on window. He brought the concept back to Harvard, where it was taken up by a young astronomer named Fred Whipple, better known to later generations for his work on comets, but in 1942, a wartime electronics researcher who had also been offered a position by Robert Oppenheimer to run the Manhattan Project's computing section. Whipple turned Oppenheimer down. He thought the radar countermeasures work was more important. The American adaptation of chaff, which was the American name for what the British called window, diverged from the British version in 2 significant ways. First, the Americans focused on dispersing many more strips per release. Whipple realized, working with Navy engineer Merwin Bly, that the more strips that could be dispersed simultaneously, the more confused a human radar operator would become. Dropping thousands of strips at once rather than hundreds was a substantially more effective countermeasure. Bly developed the critical mechanical innovation, a cartridge design that forced the strips to rub against each other on the way out of the dispenser, generating electrostatic charge. The charged strips repelled each other, dispersing into a wide cloud rather than falling in clumps. Earlier American tests had failed because the strips clumped together and fell uselessly to the ground. The electrostatic dispersal made the strips effective. The second American difference was industrial. The Americans, with their characteristic mass production approach, scaled chaff manufacturing to volumes the British could not match. By the end of the war, the American aluminum foil industry was producing chaff in quantities that allowed it to be used freely on virtually every American bombing mission over Germany and the Pacific. Whipple himself estimated in post-war interviews that the American radar countermeasures program saved the lives of approximately 600 American heavy bomber crews in Europe and 200 B-29 crews in the Pacific, a total of approximately 8,000 airmen by his calculation. For the Pacific theater, Whipple developed a variant called Rope, 400-foot reels of quarter-inch wide aluminum strip deployed via small parachutes optimized for the lower-frequency Japanese radars that the standard chaff strips were less effective against. B-29 crews deployed Rope from the unpressurized camera bay of their aircraft, releasing the long, unspooling reels into the slipstream as they approached Japanese defended airspace. One chaff packet from a B-17 over Germany could generate a radar return the size of a B-17. The packets were known to bomber crews as dehydrated bombers, folded-up false bombers that could be released through a slot in the fuselage to confuse the German air defense system into thinking it was tracking aircraft that were not there. A single B-17 might drop dozens of these packets in the course of a single mission. The arithmetic, multiplied across thousands of bombers over hundreds of missions, was decisive. The strategic effect of Window and its American successor, Chaff, is one of those things that does not appear in the standard popular accounts of the air war, but that operations researchers have spent decades trying to measure. The most direct measure is bomber survival rates. In the months before Window, Bomber Command was losing on the order of 4 to 5% of dispatched aircraft on major raids over Germany, with some heavily defended targets pushing those losses into the double digits and the threshold of operational sustainability sitting somewhere between 5 and 7%. On the first Hamburg raid with Window deployed, losses dropped to about 1.5%. Across the full Battle of Hamburg, 33 major attacks involving more than 17,000 sorties between July and November 1943, the overall loss rate ran at roughly 4%, a figure that British official histories have credited largely to the use of Window. Across the rest of 1943 and into 1944, as the Germans adapted and the British counter-adapted, losses oscillated but never returned to the worst peaks of early 1943. The bombing campaign continued. Raids that had been impossibly costly in 1942 became routine in 1944. The total weight of bombs dropped on Germany rose by orders of magnitude. The crews knew it. Across Bomber Command, the introduction of Window was received as a development that meaningfully improved the odds of getting home alive. Crews who saw it work over Hamburg flew as many subsequent operations as they could pack into the available time, on the rational assumption that German countermeasures would eventually close the gap. They were right that the gap would close. Wild Sow and the SN2 radar would take meaningful bites out of the British advantage by late 1943, but they were also right that the survival window was real and worth using. Tens of thousands of British and American airmen flew missions in 1943, 1944, and 1945 that they would, statistically, not have survived without the simple cloud of aluminum strips falling behind them. The total saved is impossible to calculate exactly. Whipple's estimate of 8,000 American airmen is probably conservative. The British figure added in would push the total well into 5 figures. These are not the kind of casualties that get memorialized at war monuments. The men who survived because Window worked do not, by definition, have names that appear on lists of the dead. They got home. They lived through the war. They had families, careers, ordinary lives, and most of them never knew exactly how close they had come to being among the statistics on the other side of the ledger. There's a parallel effect that matters as much. The German air defense system, which had absorbed enormous industrial and human resources through the early war years, was rendered partially obsolete by a countermeasure that cost less to produce than the radars cost to operate. The thousands of trained German radar operators, the hundreds of Würzburg installations, the elaborate plotting tables and ground-controlled interception protocols, all of it had been built around the assumption that the radar information would be reliable. When Window removed that reliability, the entire investment lost most of its value. The Germans kept the system running. They added new tactics. They built new airborne radars. But the original Kammhuber Line, in its original form, never recovered. There's also a longer-running consequence. The principle behind Window, that the simplest electromagnetic countermeasure, manufactured cheaply and deployed in vast quantity, could defeat the most sophisticated radar system available, was a foundational insight in what would later be called electronic warfare. The chaff dispensers on every modern combat aircraft, the chaff rocket launchers on every warship that has gone to sea since 1945, the standard NATO doctrine for defeating radar-guided missiles by saturating the seeker with false targets, all of it traces back, in a direct technological lineage, to the bundles of paper-backed aluminum strips that British bomber crews dropped through their flare chutes over Hamburg in the summer of 1943. There is a thought experiment worth attempting at the end of this story. Imagine that you are an engineer working in the German radar industry in the summer of 1942. You have spent 5 years building the most advanced air defense system in the world. You have factories producing Würzburg tracking radars by the thousand. You have an integrated network of detection, control, and interception that has been killing British bombers at rates the British cannot sustain. You are at the peak of your industry's achievement. You believe, with some justification, that you have solved the air defense problem. Now imagine that, 1 year later, your entire system has been rendered partially obsolete by paper strips coated with aluminum. Not by a more powerful radar, not by a better airplane, not by a tactical innovation requiring its own years of development, by cheap industrial paper, cheap aluminum, and a pair of scissors operating at the right cutting length. This is the experience that the German radar industry actually had in 1943. It is one of the most humbling experiences that any sophisticated technological system has ever undergone, and it has a specific lesson built into it that the entire history of military technology since 1945 has not fully absorbed. The most expensive defensive system is not always defeated by the most expensive offensive system. Sometimes it is defeated by the cheapest possible solution, deployed in vast enough quantity to overwhelm the assumptions on which the expensive system was designed. The Germans had every reason to know this in advance. They had developed Duple in parallel with the British development of Window. They had known for the entire 18 months before Hamburg that their own system was vulnerable to the same technique. They had simply, by a logic that made sense at the time but turned out to be wrong, assumed that the British would not use the countermeasure first because the British had as much to lose from a mutual deployment as the Germans did. The British, in fact, had as much to lose, until the strategic balance shifted enough that they decided to risk it. And once they did risk it, the standoff broke, and the entire architecture of German night air defense suffered a humiliation it never fully recovered from. The men who designed Window and Chaff are not particularly famous. Joan Kern's name appears in radar histories but not in popular war histories. Fred Whipple is remembered mostly as a cometary astronomer, not as the inventor of the device that saved thousands of bomber crews. R.V. Jones, the British scientific intelligence chief who identified the German radars in the first place, wrote a remarkable memoir after the war, Most Secret War, that documented the entire campaign in detail. But the book is read mostly by specialists. The story does not, on the whole, get the place it deserves in the standard narrative of how the Second World War was won. But it should, because the lesson it teaches is one of the most important lessons of 20th century military technology, that ingenuity deployed in quantity beats sophistication deployed in isolation. The aluminum strips falling through the German night sky on July 24, 1943, were not impressive objects. They cost almost nothing to manufacture. They required no advanced technology to deploy. A bomber crewman could drop them through a flare chute on a stopwatch. What they did, collectively, to the most sophisticated air defense system in the world was the kind of asymmetric outcome that engineers and strategists are still trying to learn from 80 years later. If you found this story interesting, leave a comment below. What other simple solutions to expensive problems do you think have shaped the wars and the industries of the modern era? And if you know veterans or descendants of veterans who flew with Bomber Command or the 8th Air Force during the Window era, share their stories. The men who actually dropped the aluminum strips in the dark over Germany are the ones who deserve to be remembered for what those strips actually accomplished.